studying bending stress for a quiz tomorrow. I wonder where Blue is. I'm really having a hard time. What is it, Blue? Hey, where are you going? Come on, let's follow Blue.
Here's the mail, it never fails. It makes me want to wag my tail. When it comes, I want to wail.
Wait, Mom, what's happening? I don't know, I'm scared. OMG! Let's get out of here ASAP! There's a way out! Come on! Oh, it's not! I think we need to write first the formulas for equilibrium in order for us to get out. Look at those formulas!
To complete the derivation of the texture, we must locate the location of the neutral axis of the cross-section and derive the relationship between them. Both can be accomplished by applying both equilibrium conditions. The figure shows a typical cross-section of a beam. The normal force acting on the infinitesimal area dA is dP. Substituting this equation to this, we obtain dP is equal to negative E over rho y derivative of the area, where y is the distance of dA from the neutral axis. Equilibrium requires that the resultant of the normal stress distribution over the cross-section must be equal to the bending moment acting about the neutral axis, which is the z-axis. Moreover, the resultant axial force and the resultant bending moment about the y-axis must be zero. That is, integral of dP is equal to 0 and integral of dVP is equal to 0.
The equilibrium equations were developed. First, the resultant axial force must vanish. The condition for zero axial force is the integral of dP is equal to the negative of E over rho times the integral of y dA is equal to 0. Because E over rho is not equal to 0, the equation can be satisfied only if the integral of y dA is equal to 0. Then, the resultant moment about y-axis must vanish. This condition is the integral of z dP is equal to negative E over rho times the integral of zy dA is equal to 0. The integral of zy dA is the product of inertia of the cross-sectional area. Lastly, the resultant moment about the neutral axis must equal m. Equating the resultant moment about the z-axis to m gives us the negative integral of y dP, which is equal to E over rho times the integral of y squared dA, which is equal to m.
Hey, what's that? We have successfully correct the moment curvature relationship equation. We can finally get out! Oh, please!
A clue! A clue! A clue! A clue!
Our first clue is a rectangle. Ano yung pas mo? Hi, it seems that you have a problem.
Yes, I have a big problem. I'm having a hard time memorizing all these formulas and tomorrow is our quiz.
Oh, that's a big problem.
I think I'm giving up.
No, we will find a way to help you. What can we do to help you easily memorize the formula? Yeah, that's right, mnemonics.
But how can we make mnemonics?
For the first formula, remember this mnemonic. Stress is not my imperfection. For the second formula, O my chocolate ice cream. For the third formula, O my sweetie pie. And that's it. We derive mnemonics for the flexure stress and other flexure formula.
A clue! A clue! A clue! A clue!
Our second clue is a beam with the hinge support and the roller support. Oh, I wonder where Blue went. I think someone needs our help.
Steve!
Hello, Mr. Triangle. Why are you crying?
Well, you see, me and my friends know something very dear to us.
We lost our formulas.
Why are those formulas important?
These formulas will help us compute the moment of inertia of the cross-sectional area. Can you help us, Steve?
Oh, I love to, but can you help me find Blue?
Sure, Steve. Yes, thank you so much.
You first, Mr. Rectangle.
Well, my formula is very simple. It consists of my base multiplied by my height squared divided by my favorite number, which is number 6.
Is this your formula?
Yes, Steve. Thank you so much, Steve.
Go.
Your third solid circle.
I love pi. Sometimes I use radius. Sometimes I use diameter. My radius cube is paired with 4, while my diameter is paired with 32.
So, I guess this is your formula.
Yes, Steve. Thank you.
So, how about you, Chu?
Well, my formula consists of 2 radius, the inner radius and the outer radius. My favorite number is 4 and it consists of pi. So what is my formula?
Is this the formula you're looking for?
Yes, you're right. My turn, Steve. My formula is the same as rectangle's formula, but instead of 6, my favorite number is 24.
Oh, here you go, Triangle.
Thank you, Steve.
Thanks for your help, Steve. By the way, I saw Blue went that way.
Well, thank you.
A clue! A clue! A clue! A clue!
Our last clue is a distributed load. The 3 clues, the rectangle, the beam, and the distributed load. I wonder what this means. Right! Blue wants to solve a problem on bending stress.
We just figured out Blue's clues. 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 'Cause we're
In drawing the shear diagram, we will start first at point A. Since at point A, the force is 14 kN directed upward. That's why we draw here upward with 14 kN. Second, in the segment A and B, since the system is uniformly loaded, it is drawn diagonally downward. The value is 9.2 by getting the force 6 kN that will be multiplied to 0.8, which is the distance. And the value we will be getting there will be subtracted from 4 kN. That's why 14 minus 4.8 is equal to 9.2. At point B, there is a force 15 kN downward. That's why in the shear diagram, we drew a force downward. At point E, there is a force 19 kN upward. That's why again, the shear diagram, it will just go back to 0. Segment DE, we will get a value of negative 19 by subtracting the product of this distance, which is equal to 1 meter, and the force 6 kilonewton. The value of M0 is equal to 0. We get 9.28 by adding MO, which is 0, and the area 1. We get the area using the formula of the trapezoid, which is 1/2 multiplied to h1 plus h2 times the base. We get 16 by again doing the same process we previously did. So M1 plus A2 equal to 16. M3 it will just go back to 0. Having the rectangular cross-section 120 millimeters wide and 200 millimeters high, we can get the moment of inertia of the cross-section about the neutral axis. And the formula is I is equal to B h cubed over 12. Substituting the values, I is equal to 0.12 times 0.2 cubed all over 12. And the answer will be 80 times 10 to the negative 6 m to the 4th. Bending moment we got in drawing the moment diagram will be used in obtaining the maximum bending stress in the beam. Substituting the values, we will get the Mmax from the moment diagram, which is the highest point, 16. C is the distance of the top or bottom from the neutral axis, which is 100 millimeters. And I is equal to 80 times 10 to the negative 6 m to the 4th. And the answer will be 20 times 10 to the 6 Pascal. In drawing the figure, we are guided by the following observation. First, bending stress varies linearly with distance from the neutral axis. Second, the maximum bending moment we have solved is positive. To get the bending stress, we will use the formula the value of M is 9.28 times Y, which is equal to 0.075 meters all over the moment of inertia, which is equal to 80 times 10 to the negative 6. And the answer will be negative 8.7 MPa. The negative sign indicates that it is compressive.